battery backup sump pump system in a home, and we want to check the status of this battery. One of the earliest ways of devising a means to check the state of charge of a battery is to use just a simple voltmeter. What you're seeing here is a voltmeter attached to the plus and minus of a battery. The only way that this will work is the battery has to be totally unplugged from the device for a minimum of 24 hours. So I let this one sit for 2 solid days, put the multimeter to it, and I read 12.2 volts. This is not a very precise measurement, but it gets us a relatively close state of charge. There are a variety of chemical makeups and plate compositions that are used for lead-acid batteries. In this particular type, we have a true deep cycle battery. Unlike a maintenance-free battery in a car, a starting battery, it's going to lack a little bit of calcium and some other additives to it. Here is just a very rough ballpark for what it is. 100% state of charge would show that that voltage is somewhere near 12.6 volts. Somewhere near 12.45 volts for all 6 of the cells collectively would be about 75%. This voltage that we read here is 12.2 volts, which is right under 50%. So this battery's got a 50% state of charge as measured by the open voltage reading here. So this is a totally floating battery. It cannot be measured in a closed circuit, meaning there's loads hooked up to it. The next step that some people will use to measure the state of charge of a battery is a hydrometer. And the hydrometer is a other predictor of making measurements with it, and it will only work for a select few nickel-cadmium batteries, but predominantly these flooded lead-acid batteries. As the state of charge increases, that battery's accepting electrons into it, the sulfuric acid generally becomes a little bit heavier. That the specific gravity of that solution should increase. The sulfuric acid removes itself from the electrolytic and binds to the plates, forming lead sulfates, and that density becomes lighter and more water-like as that specific gravity gets lower. We could use a hydrometer to do that, or, like what we're going to do in this lesson, is use the refractometer that we just did the demonstration on a few minutes ago. So we get that orange glycol battery tester. The first thing that I did is I removed the battery from the loads. I measured the voltage just to give me a relative strength of measurement. And then what I did is wearing proper safety apparel. So remember, with sulfuric acid on batteries, gloves, plastic aprons, safety glasses, and a face shield should be used. I've watched many of these silly videos on YouTube and other places, and you always hear people talk about it, but usually it's a good talk, and you don't see the people backing it up by actually wearing the proper protective wear. So I'm bringing it to your attention, A, to save my butt, because this is the proper way of doing it, and B, it's just good practice to get into good habits all throughout whatever measurements and safety items that we're talking about. First thing is I remove the cap. The second thing then is I take this orange stir and I gently reach in to the side where the lead plate is and try to get a drip of that sulfuric acid. I then place that drip on that slide that is on the refractometer and I read it. So the very first reading that I read is this device. Now some of the next couple of pictures won't look as pretty as this, but you get the point. So for the very first cell, I have a specific gravity of 1.2, and it is just at that recharge and fair state. If I just went by the state of charge, it said it was at 50% charge. Here the state of charge and the density that is being measured by the refractometer is telling me it's a little bit less and it's time to charge that battery up. So that's the first cell. Just remember it's right at 1.2. The second cell, so again I took the orange stick, I cleaned it off, I cleaned with a tissue the second one, and this is a little blurry, it was difficult to get the pictures perfect, but you can see that we're right at the same level for cell number 2. Cell number 3, better picture, but notice its density is different. See, here's the problem that happens. The chemical makeup of each one of these cells is going to behave slightly different, and because it behaves slightly different, they're not going to all have the same exact state of charge. That will be a problem later for us when we start putting batteries in series. And then once we put them in series, we may have to stack them in parallel to give us the proper amp hour rating that we need. And so the ballpark is we generally don't want to do more than 3 banks in parallel. And the reason for it is this particular sealed lead acid has 6 cells for 12 volts. Larger traction batteries will only have 3 cells for 6 volts, and then we would put, say, 2 of those traction batteries together in series for 12. But you can see that the density here, and the refractometer is telling me it's got a different density of that. Now I go to the next one, and it's the same characteristics there. And I don't know if I've got more because they were too blurry on me trying to get these images, but you have to do all 6. And what I've seen over the years is as I do a measurement and a battery goes bad, I will see one cell just be totally off. And usually that tells me that that battery has been frozen or it's been abused, or there's been some sort of internal damage done to a particular cell. So if you see them all within the same range, but say one's way out of the ballpark, that's a good indication that that cell is indeed bad and the entire battery is bad. But in this case, after sitting for 2 days and not being charged for a long time, it's got a state of charge of that, and it looks pretty decent. So I'll put the cap back on, and now I have measured the state of charge for that